Welcome to PowerUp, a podcast show hosted by Maurizio Di Paolo Emilio that brings life to some of the stories on power electronics technologies and products featured on powerelectronicsnews.com and through other AspenCore media publications. In this show, you'll hear both engineers and executives discuss news, challenges and opportunities for power electronics in markets such as automotive, industrial and consumer. Here is your host, Editor-in-Chief of Power Electronics News and Embedded.com, Maurizio Di Paolo Emilio.
Hello everyone and welcome to this new episode of PowerUp, where we will talk about next-gen power architectures in solar. Today's episode is brought to you by our sponsor, Renesas. Power conversion is undergoing a radical transformation as electrification expands across sectors like solar energy, electric vehicles and smart grids. The focus is shifting toward architectures that are more efficient, more compact and more intelligent. Trends like fewer conversion stages, higher voltage buses and bidirectional energy flow are reshaping the design landscape. Today, we are focusing on a critical area, solar energy conversion, and how innovations are pushing the boundaries of efficiency and integration. The industry is rapidly evolving, driven by the demand for smarter, more compact, and highly efficient energy systems. In this conversation, in this podcast today, we speak with Marco Ruggeri, Senior Manager of the Power System Architecture team, and Pietro Scalia, the Head of System Application and Marketing for Power, both of Renesas Electronics, who are at the forefront of this evolution. They will share insights into Renesas single-stage bidirectional GaN-based microinverter and how it could redefine the future of energy conversion and distributed power systems. Let's talk with Marco and Pietro.
Hi Marco, hi Pietro, thanks a lot for being here. How are you?
Hi Maurizio, all good?
Nice to be in the call.
Thank you so much. So where are you located, Marco and Pietro?
I think we are both in Munich, Germany.
Yes, this is where basically Renesas power system marketing and architecture is kind of the worldwide hub. So we drive this activity worldwide, but we are based in Germany, in Munich.
Good. So as I mentioned at the beginning, we will talk about power architecture in solar systems and related topics. So before that, let's start introducing you. So please give us a bit of your background and current activities at Renesas. Pietro, and then Marco.
Okay, so thank you, Maurizio. Again, I am leading inside Renesas the power system marketing and architecture. Our team scope is basically to support the entire portfolio across all the regions, all the product lines. And it's a systematic approach, so we are experts in end equipment and applications. We work specifically on some key topics, key market trends. Solar today is one of these. And my background, let's say I come from other semiconductor. It's been a long journey. I have been working for TI for more than 10 years on semi in the past, dealing most with EV traction. At that company, at TI, has been very horizontal role, pretty similar to this one. And let's say later on, actually, there is a background in telecommunication or let's say communication infrastructure, which today comes very sound because we live the hype of the AI and the data centers, which is, of course, resonating a lot with my past in Ericsson and Nokia before joining the semiconductors.
Thank you, Pietro. Marco.
Yeah, so I'm currently leading the power system architecture team in Renesas. My team focuses on the advanced development of different reference designs in multiple applications. We do cover the AI data center and infrastructure power, the new energy and the motor driving applications. I started my career a while ago, I would say, at Intel here in Munich, where I was working on signal and power integrity topics for the 3G modem at that time. And then that, I've joined Dialog Semiconductor, where I've been working on analog design and modeling for PMIC and all the different kinds of DC-DC converters. I was part of STM, where I was working on wireless charging. And finally, I joined Renesas a few years ago in the automotive system team, focusing on the ADAS power supply, so ultra low noise supplies, and also on the powerful SoCs, which are elaborating all the data coming from the ADAS sensors. Then I think I took the leadership on this role, on this new team a couple of years ago, and I'm very excited now to work on these advanced architectures and provide great performance to our customers.
Thank you, guys. So you are expert in terms of power electronics. The power electronics field is shifting very fast, driven by different topics: electrification, renewable integration, and demand for smarter, more efficient systems. So we are talking about solar energy, for example, electric vehicles, but in all of these, efficiency, power density, simplicity. So all of these are expectations. So we are seeing a move toward fewer conversion stages, as I mentioned at the beginning, higher voltage buses. So a major investment push in terms of bidirectional and modular architecture. So all while minimizing sites and maximizing the control. So from your perspective, Pietro, so my first question, what are the dominant megatrends shaping power conversion today, and how are these trends influencing the way we design and deploy next generation energy systems?
I think the power conversion scenario has been definitely reshaped by the advent of wide bandgap. This includes, let's say, generation to storage to transport of energy and utilization of different, from automotive to data centers, as we said before. And I think the wide bandgap brought basically a change in topologies, most simplification, in the sense that the new power components could implement big changes that at the end improved efficiency and power density in all the high, let's say, demanding application, as we said, from grid forming to EV to data centers. And specifically, if we go to topology, we started to see elements like increasing of the bus voltages, a less number of conversion stage, again, to increase efficiency, the use of bidirectional topologies and modular architectures. And the components come along, so specifically wide bandgap GaN, in our case, can enable a lot more compact and higher switching frequency design. And of course, together with digital control, which gives the intelligence, I think this has created a lot of optimization of the BOM of these converters. At the end of the story, also in terms of cost, because if you can simplify the topology and use less switches, of course, the cost benefits. There is a side aspect of this. There are also topics to be solved, like thermal management, so new packages are needed. EMI compliance is typically a topic, and a life cycle, because wide bandgap, of course, had to develop a lot of new process to guarantee the same quality or even better than before. I think there is no one solution fits all. I think the word holistic approach across each stage of each converter is important. So MOSFET are still alive, IGBT, SiC, and GaN, of course, find sweet spots. I think this is important as a trend. At the end of the story, the user wants to have the best efficiency, as we said before, in the best power density.
Thank you, Pietro. Great. So, Marco, Pietro mentioned different mega trends. In particular, efficiency. So this is not just a design choice. It's a system level shift with huge implications from different point of view, sites, reliability in particular. So you are working on a single stage dual active bridge based microinverter using a bidirectional GaN architecture. So what advantages? So please tell us more about the advantages over the traditional flyback plus inverter architecture. So your solution will combine DC-AC and AC-AC systems in just one platform. So can you walk us through the core architecture of this single stage converter?
Sure, Maurizio. Our dual active bridge based microinverter architecture consists of a full bridge network using our 100 volt REFSFET silicon MOSFET that are converting the solar panel low voltage DC output into an high frequency AC input from the primary side of the transformer. At the secondary side instead, we leverage our new high voltage 650 volt rated bidirectional GaN devices that converts the AC transformer output into the grid voltage, forming the actual grid. So this architecture directly converts the DC to an AC with a pretty small and compact BOM count compared to the existing flyback plus inverter structure. It will also increase the overall power density. It's probably one of the major advantages here. And talking about efficiency performances, the single stage topology is able to exceed 97% peak efficiency, 97.1%. So this is an astonishing result compared to the standard one, where the combination, the cascaded architecture of the flyback plus the standard unfolded inverter typically achieves 92 to 93% efficiency from panel down to the grid.
Great, thanks, Marco. So, Pietro, one consideration that we can highlight is so you are aiming efficiency, increasing both efficiency and reduce sites on the same time, simultaneously. So this is a difficult combination to achieve. So how are you managing that trade-off? So we are talking, as Marco said, peak efficiency of 97%. So what are the primary design strategies and innovation from technical point of view, such as zero voltage switching and the approach to the single stage conversion that enable such high efficiency figures in the DAB based microinverter?
Yes, Maurizio. So we mentioned already two key elements. On one side, the simplification of the topology, and on the other side, the use of this new element, the bidirectional switch BDS GaN. So let's go a little bit more into the physics of the device. It's a lateral device like today most of the GaN devices available. And I think the device has a fantastic dissipation capability to the substrate. It's a source down structure, right? But we have packages that can also enable bidirectional dissipation, top and bottom. The device shows basically a virtual no reverse recovery and the possibility of a very fast switching. In that sense, we reduce basically most of the losses, switching losses, and most of the dissipation is due to conduction one. So I think in that sense, we can even operate in hard switching and still seeing a big benefit versus the conventional material. But on the other side, if we implement ZVS, we estimate in this specific topology about 1%, a little bit higher than 1% efficiency improvement. So we have ZVS at full load. At light load, we need to implement other strategies like pulse skipping. And if now we leverage this device for our customers, we implement the family approach. So we have devices that we will release this quarter, which are basically suitable for several hundred watt, but we have a family now scaling up to a couple of kilowatt, and this family will be almost released seamless starting now, basically till the first quarter of next year. This is important from 110 million down to 70 million to support again from 500 watt to kilowatt level.
Thanks, Pietro. So, Marco, may you explain the choice of components, in particular the GaN device, the role of controller in this architecture? So, how important, how critical is the controller to performance?
Sure. So, as Pietro said before, the GaN enables a pretty high switching frequency operation that in turn will significantly reduce the magnetic component size. Therefore, we are going to enhance significantly the power density. So this specific architecture, the cycloconverter topology, typically exploits a back-to-back switching scheme at the secondary side of the transformer. So one single Renesas bidirectional high voltage GaN switch can replace two standard power transistors, reducing the power stage size, but at the same time increasing the efficiency, performance, and improving the cost figure. So we can potentially improve the performance by reducing the cost, which is quite a good result for the industry. For sure, we save the cost of two transistor in series, having half of their own, and this will have also a clear benefit on the total gate charge, which would be significantly reduced as well. So in this single stage architecture, the controller definitely plays a crucial role. And in order to achieve the ever stringent EMI and THD standards at the moment, typically below 3% for this kind of application, a tight current control mode is needed. And at the same time, we need to perform current monitor on a cycle by cycle to ensure a safe and reliable operation of our microinverter.
Thanks, Marco. So, Pietro, so I have a question for you. Let's talk about GaN, as we are talking on PowerElectronicsNews.com. So GaN is approaching very fast, continues to redefine what's possible in high frequency, high efficiency, and you are going a step further. So not just using GaN, but implementing a bidirectional topology of GaN, which opens the door to reversible power flows and even more compact design. And this is important, as you know, this plays directly into the needs of smart grids, vehicle-to-grid, integrated solar, with storage systems. So how are you leveraging bidirectional GaN in this design? So what impact would offer, so would have on the system behavior, talking about switching losses and overall performance compared to traditional ones?
Yes, like we said, this bidirectional switch brings definitely a revolution right into the topology implementation, and we leverage this to enable basically compact design that swing from smart grid, vehicle to grid, integrated solar and storage system. Basically using this ideal for a quadrant switch, right, we eliminate the need of back-to-back switching stages. This means that we simplify the architecture a lot and the BOM. And we have used this into AC-DC as well into DC-AC. We have 650 volt rated devices in topologies like Vienna rectifier for three-phase. For example, we don't need to have multi-level approaches. Therefore, we can reduce the size and cost for this converter. Overall, the reduced number of switches increases as well the possibility of the let's say less point of failures of the entire converter. So this gives you the value in terms of size. It gives you a compact, reliable, and high efficient system that let's say can give to you definitely flexibility to implement structures like grid interactivity, energy flow that you can manage for modern, let's say, flexible power systems.
Thanks, Pietro. So, Marco, you are also exploring a multi-port converter architecture for hybrid inverter topology with the goal to eliminate the low voltage DC bus. So this is sounds like a simple, radical simplification. So can you explain a bit about the concept behind this one, advantages, and what kind of interest are you getting from the market?
Yes, absolutely. Let me introduce first the today most common topology. So the existing hybrid inverter architecture uses a low voltage DC bus, typically 75 volt, where both the solar panels and the energy storage systems are connected together. An isolated DC-DC converter is cascaded afterwards to generate an high voltage bus, typically 400 or around 400 volt, which is also helping into providing galvanic isolation. And this 400 volt is finally fed into a grid-tied inverter. What we are instead proposing, so it's a multi-port based hybrid inverter, which consists of a multi-port isolated DC-DC converter with 2 or even more ports, where the solar panels and the energy storage system can be independently connected to. So this multi-port converter will directly generate the high voltage bus and to feed the grid-tied inverter, reducing the total number of conversion stages from 3 to 2. Similarly to the microinverter, we will be able to reduce the solution size, but at the same time increasing the total system efficiency. We have started the promotion of this concept at the major hybrid inverter manufacturers, and they were all impressed by the architecture, and they were showing a genuine interest in our proposal, and also in power discrete technology that we showcased in both silicon MOSFET and GaN.
Great, thanks, Marco. So, Pietro, this is a platform. This is not just a proof of concept. It's a platform that will begin actively benchmarked and positioned to go head-to-head with existing market leaders. So, tell us more about benchmarking results. What early benchmarking results can you share? How do you see this technology for the future, also against conventional multi-stage solutions? And if you can walk us through the development timeline and what you are expecting in terms of lab data or initial benchmarks.
Absolutely, Maurizio. As you said, this is a platform, right? And I think even if we don't come first, let's say, into the market, I think we are now in good company, but we are coming, I think, with a good lot of application collaterals. So specifically, we have completed already the evaluation of the EV kit boards that we are right now delivering to our, let's say, tier 1 customers already. The prototype of the micro inverter is in manufacturing today, and we expect to have basically results available next month. And I think at that point, this together with the release of the part, like I said, at the end of this quarter, will complete our launch of this kind of device. And I think it's important the word platform, right? Because this is not just for solar energy. As you understand, the bidirectional, it's really a key architectural element that enables many more topologies. So what we are doing right now opens basically other approaches. We are working on AC/DC single stage for a vehicle to grid. We are working single stage in data centers to simplify the sidecar rack. So this is definitely a big approach that brings Renesas as a key partner, I hope, for our customers with this kind of architectural elements.
So, thank you, Pietro. Marco, let's understand which are the most compelling practical benefits that this solution would offer for system designers working on solar installation. So, in particular, what about the 40% reduction in weight and volume, along with, as Pietro said, reduce BOM cost? So how this will translate into tangible advantages for deployment and competitiveness?
Sure, Maurizio. Great question. For solar system designers, a 40% reduction in weight and volume, together with a lower BOM cost, translates certainly into great real-world advantages. This goes without saying. So you can imagine lighter, more compact single-stage converter can simplify significantly the wiring, the installation, especially on rooftop or remote locations. It will reduce the labor and the logistic cost, and also the amount of structural support. On the other end, for the microinverter manufacturers, the reduced component count lowers certainly the procurement complexity. So coming after the pandemic, we all know how this is important today, and speed up the assembly and improves the long-term system reliability as we are minimizing potential failure points. We also need to consider that high power density allows for more energy output in the same or smaller footprint. So we will maximizing the net power extracted from each photovoltaic panel, and we will improve the overall system return of investment. On top of that, these benefits will help accelerating the project timelines and will enable faster time to revenue. As you also pointed out, in a competitive market like that of renewable energy, the ability to offer smaller, more efficient and cost-effective systems is a key differentiator, especially in residential and decentralized solar deployments.
Thanks, Marco. So, Pietro, let's talk about scalability. So, are there plans for other further power scaling? What about the concept of providing scalable solutions to be applied for future innovations?
Yes, sure, Maurizio. This is actually what customers ask, right? We are working together with them to scale this from, let's say, a few hundred watts up to several kilowatts. And I think packaging is one of the key elements, because we are working, of course, in parallel to the improvement of the generation. Right now we are in generation 4, which shrinks the die, of course, provides better RDS(on) per millimeter square. But the topic there is how to encapsulate a very large die, because we want, of course, to have the best power density into innovative package. In that sense, I think there is a space to some novelty package to come to life. We are working on that, but we are also working on technology, because there are elements like short circuit protection where we would like to bring basically GaN to same area like IGBTs today, and to bring basically GaN into potential vertical gate structure, which is also possible to mitigate some of the bottleneck of the very large die of a lateral structure.
Thank you, Pietro. So I am almost in conclusion with my questions, so I promise. So just last 2 questions, one per each. So Marco, looking forward, so the final question for you: how do you see Renesas' role evolving in the energy conversion ecosystem and storage ecosystem as well? So especially as efficiency and integration become more critical.
Yes, sure. So on top of this application targeting, solar power, our system architect team, which is based in Bangalore, is designing multiple POCs, proof of concepts, for a lot of different applications, ranging from energy generation to energy storage and different type of utilizations, with the same goal of maximizing efficiency, but at the same time increasing the power density. We partner with our customers to support their design activities and make their life easier.
And Pietro, for you, any message that you would like to share, and takeaway for designers?
I think the very relevant final message from my side is, again, about system approach and solution. I think we live a new era in semiconductors where the value proposition is providing customers 360-degree support and trying to solve their real design challenges. And Renesas, I think, stands very well with flexible approach, rapid engineering support that the market requests right now, while we still deliver, of course, the Japanese quality that comes from our legacy. I think these are our 2 key values that the customer value.
Good. So thank you so much, guys. Thank you, Marco. Thank you, Pietro. I will see you in some parts of South Italy, and stay in touch. Thank you.
Thank you so much, Maurizio.
Thanks a lot, Maurizio.
This episode of PowerUp was brought to you by Renesas. Thank you very much, Renesas, for sponsoring us. If you want to learn more about Renesas solutions we have been talking about today, please check the links on the podcast page at eetimes.com or powerelectronicsnews.com or the Renesas homepage renesas.com. Thank you.
That brings us to the end of this episode. Stay tuned for more news and technical aspects about power electronics. If you are listening to this on the podcast page at eetimes.com or powerelectronicsnews.com, links to articles on topics we have discussed are shown on this page. Power Up is brought to you by Aspen Core Media. The host is Maurizio Di Paolo Emilio and the producer is James Eade.